Hello and welcome back everyone. In this video we're going to talk about the normal distribution, which is another kind of random variable, and particularly a continuous random variable. We're also going to talk about what is called the sampling distribution, which is something that relates nicely to the normal distribution, and that will effectively cover off the first half of the course, which we could broadly describe as descriptive statistics and probability theory. And then when we come back after the test, we will go and start talking about the second half of the course, which we could call inferential statistics. So before we get into talking about the normal distribution, we should talk about what the test is going to look like. So the test is scheduled to be done on March 1st, and I'm going to make a proposal for how we should do it. And I'm open to suggestions, feedback, comments, criticisms, or anything really in regards to this. So what I propose is that I write up a test that is somewhere between 8 and 12 questions that would look kind of like the homework or potential quiz questions, and that would cover anything up until and including this video. I would also plan on making the test both open book / notes and also open to R. So I was thinking about how to do the test, and originally I was thinking that I didn't want to have anything involving R, but in thinking about it more, for a lot of the questions that we would have to do with random variables, the options would be effectively, I can include a bunch of probability functions in the same way that I just did for the most recent quiz, and that would work fine, but I just don't really see the point in necessarily doing that, because if you were doing any kind of statistical analysis for any future coursework or research project or something, you'd probably just be using a statistical package like R anyways, so you may as well get used to using it. So what I'm thinking I would do is allow you to use R, and then I could go and ask you very similar questions to what we just had for the last quiz. And it would then come down to a matter of you being able to read a problem and recognize what kind of probability distribution you're looking at, and also the appropriate function to use. So I would go and include a reminder of what each of the functions does. So I would include a reminder that D followed by your probability distribution will give you the probability mass or probability density function at that given value, and then P followed by whatever your probability distribution is will give you the cumulative mass or the cumulative density function. So the probability that you get a value that is at most the argument you give. So I think that would be a fair way to do it. You wouldn't have to write anything profound in R. I wouldn't ask you to do anything like on the homework where you had to go and sample from the event of throwing 3 die and summing them together. You wouldn't be asked to do anything like that, but you could use R to help with probability distributions and things like that. So instead of having to punch the various function results into a calculator, you could just go and use R to do it, and I think that would be a fair way to do things. Um, you also couldn't use any external resources like Google, Wikipedia, or anything. You couldn't use anything like that. And what I would do is I would make the test due by Wednesday, March the 3rd. So you would have um, 2.5 days to complete the test. I wouldn't put any time limit on it, so you could treat it as effectively a homework assignment where you have about 2.5 days to do it. So I think that is a fair proposal for how we could conduct the test, but if you have any criticisms, suggestions, I am open to possibilities. I would like to have everybody who wants to give an opinion on this matter do so within about a week or two, so that way I could get the test written by at least the last week of the month. Um, that way I can at least have enough time to make sure that it's reasonable. Okay, so then the other thing that I want to kick ideas around for is the project. So what I propose is that by March 1st, everyone have a dataset or a proposal for a dataset. If you don't have a dataset that you can get your hands on, but you have an idea that you want, and you'd like to see if I could go and try and rig something up for you, have at least a couple of ideas, because depending on what you pick, it might be that I can't come up with anything for you. So do have backup plans in mind. If you have a data set, um, do let me know what it is, because it could be you pick a data set that's kind of trivial and you wouldn't be able to do anything really with it. If you want, you can do this project in pairs. I don't have a problem with that. The problem might be that, given any restrictions that you would have to be under due to the university or the government or whatever, it might not be overly practical, but if you want to do it, I don't have a problem with it. One thing that you should do, and I highly recommend that you do this, is look ahead a little bit in the textbook. So at this point, we have covered, after today, the first 7 chapters. Take a look at what we're going to do coming up. The other thing to point out is that this is going to be the last video that we're going to have for a month, because next Monday is the Family Day holiday, so we don't have class next Monday, so there won't be a video for next Monday. Then on the 22nd, I'm just planning on treating that as a review day. And if you have any questions, hop into the Zoom call and let me know, and we can do that, and then I'll have my typical Zoom calls throughout the week. And then the test will be on March the 1st, so we won't have any class videos until the 8th. So you'd have a full month to go and kind of skim ahead and look at what we're going to be doing after we come back from the test. So for the remaining weeks in March, and then I guess the first couple in April. So you don't necessarily have to have a good knowledge base of what we're going to be doing, but if you look at what we're going to be covering, that could give you some motivation or give you some ideas about a potential project problem. And then what I propose is by March 15th or maybe a day or two later, so that way you could see what we've done the first 2 weeks after the test, have a formal problem that you want to go and investigate. It could be a couple of different problems, but at least have one that you want to investigate based on your data set. I will set a formal deadline for submission by the 21st of April. So that is the final day of exams. So that would give you a full month and a little bit to go and write up whatever you need in R, and then also write a summarizing report. What I might go and do is provide a reference to a project for a multivariable statistics course that I did. So the techniques that would have been used there would be things that we're not going to cover, but that could give you maybe a broad idea of what you would want a project to look like. So you would take a data set and just think of something that's worth investigating. And then if you look ahead a little bit, you could see some of the techniques we're going to use, and maybe that could motivate a question to ask that you could investigate. Okay, and again, with this, I'm also open to ideas and suggestions if you have any, so please let me know your opinion on these matters, and we can all kind of collectively come out with something in the end that'll work for everybody. Okay, so now let's get into the main topic for today. So we want to talk about the normal distribution, and the normal distribution we define in terms of 2 parameters. Mu, which is this first letter that kind of looks like a U with a stem on the left side, and a sigma, which kind of looks like an O with a bit of a stem coming out on the right, sigma squared. And for a normal distribution of mu and sigma squared, the expected value for this random variable is going to be mu. So the mu describes the mean for the distribution, and the variance for our random variable is sigma squared. The probability density function for a normal variable is given here. One of the nice properties of the normal distribution is that it's symmetric. So if we were to fold the normal distribution over at the mean, we would get the same thing on both sides of the mean, and we'll see some pictures of normal distributions coming up in a moment. And with normal distributions, we could talk about an x value being within so many standard deviations of the mean. So here, if we have a normal random variable where our mean is mu and our variance is sigma squared, or our standard deviation is just sigma, we would have that the probability that x is within one standard deviation of the mean, so it's at least the mean minus a standard deviation, but at most the mean plus a standard deviation, that probability is going to be about 68%. The probability that x is going to be at least the mean minus 2 standard deviations, and at most x plus 2 standard deviations, is a bit over 95%. and the probability that x is going to be at least mu minus 3 standard deviations and at most mu plus 3 standard deviations is getting very close to 100%, but it's about 99.7%. Okay, so depending upon the mu and sigma squared values that you give, you get some rather different looking probability distributions. So what we have here is the probability density function for 3 different normal distributions. So the blue curve describes a normal random variable with mean 0 and standard deviation 1. So what we can see is that if we were to take that blue curve, and we could ignore the red and the green ones for the moment, and we were to just go and fold the negative values over onto the positive values, the normal distribution would give us the same thing. In other words, if we put a mirror down at x equals 0, the left side and the right side, we would just get a mirror image. What we see with the red curve, so a normal distribution with mean 1 and variance 2, is that it looks a little bit flatter, or it's kind of wider. There's more variation going on here, and we've also shifted everything over by 1 unit. So that for the red curve, the mean is at 1. For the green curve, we put the mean to be minus 3, and we've made the variance 0.5. So what's happening there is there's not as much variation, so all of the values are much closer to the mean than they are for the red curve, so the normal 1, 2 normal distribution. Okay, so one of the other nice properties about normal distributions is that we can effectively just talk about a single normal distribution, because we can kind of take any normal distribution and reframe it as a normal 0, 1 distribution. So if x is a normal mu sigma squared random variable, we could take z to be x minus mu divided by sigma, and that will always be a normal 0, 1 random variable. We could go and see a quick example of this. So suppose that x is a random variable that's going to be normal with mean 3 and variance 49, or standard deviation 7, and we want to know the probability that x is at most 10. What we could do is standardize our x and then look at the probability for the standardized value. So we'd first want to go and standardize the value of 10. So we'll take 10, we'll subtract off the mean of 3, so we'll get 10 minus 3 for 7, and then we'll divide by the square root of our variance. So we'll divide by the standard deviation, which in this case is nicely 7. We could think about 10 in the coordinates of our x random variable as 1 in the coordinates of our z random variable. So you could kind of think about this in the way that you would work a high school algebra problem where you would want to go and transform a function. So suppose you had something like the plot of sine of x, and then you were asked to make the plot of sine of 2x minus 3 based on your plot for sine of x. It's the same kind of idea. You're doing a transformation of your variable x into something that's in this case nice and standardized. So here what this says is that the probability of getting x to be at most 10 is the exact same as the probability that a standard normal random variable is at most 1. And in this case that's going to be about 84%. We can also talk about what's called the central region for a, in particular, normal random variable. And this is going to be the region of the x-axis that's going to contain the what we'll call the middle 95% of the area for the random variable. When we start doing more inferential statistics, we'll see this show up more and more. So if we were going to look at this in terms of R, the function qnorm will be of use here. So remember that last week when we were going and looking at random variables in R, I'd said there were 4 different prefixes. Last time we saw D and P, so D gave us the probability mass or probability density function, and P gave either the cumulative mass function or the cumulative density function. What Q is going to do is give the reverse of P norm. So you could think about this in effect as a Jeopardy kind of question. So if you go and give P norm of X, what that is saying is what proportion of the area is to the left of X. With Q norm, you give it a value, so here we'll take Q norm of 0.025 and we'll take the mean and the standard deviation to be 1. And what that is asking for is what is the X value so that 2.5% of the area is to the left of that X value. And what we would have here is that at about minus 1.96, about 2.5% of the area for the normal distribution is to the left of minus 1.96. And then we would also want what is the x value so that 2.5% of the area is to the right of that value, or 97.5% is to the left, and that would be about 1.96. And that makes sense because we said normal distributions are symmetric. So here we could go and look at a shaded region for a standard normal 0, 1 random variable. And what we have here is that the shaded gray region is covering 95% of the area for a normal 0, 1 random variable. And what we see is that the left edge for the gray region is at about minus 1.96, and the right edge for this gray region is at about 1.96. And when we open up R, we'll see a little bit more about these. One other nice property of the normal distribution is that you can use it to approximate other distributions. So suppose that we took a coin, we flipped it 5,000 times, and we wanted to look at the number of heads we got. So that would tell us that our random variable x would be distributed as a binomial 5,000 and 0.5 random variable. So 5,000 trials, so 5,000 is our n, and our probability of a success, or getting a heads, is 0.5. And what I've done here is taken a plot of all of the particular values between 2400 and 2600. So we get the probability of getting every value between 2400 and 2600 heads. And what we see here is that this really looks a lot like a normal distribution. So we compare it to that. Those two curves look very, very similar. And what actually happens is that the normal distribution can be used to approximate the binomial distribution. So remember that the expected value for a binomial distribution is just the number of trials times the probability of success. So in our case, that'd be 2500. And the variance is going to be the number of trials times the probability of success times the probability of failure. So n times p times 1 minus p. And in this case, that would be 1250. So what I've done is I've taken the probability mass function from a moment ago, and I've overlaid it with the probability density function for a normal 2500 and 1250 random variable. And what we see is there's basically nothing to choose between the probability density function for the normal random variable and the probability mass function for the binomial random variable. Okay, so this works kind of, as we can see from the picture, pretty well when n is going to be large. And also p makes things so that we get this nice shape showing up. But we could look at other examples where the approximation doesn't work so well. So here we're going to go and take the roll of a die 30 times, and we're going to look at the number of times we get a 6. So here we're going to have our random variable is going to be a binomial random variable with 30 trials and probability of success equal to 1/6. And we get the plot of the probability mass function here. So what's going on here is we have the probability of getting 0 sixes, the probability of getting 1/6, the probability of getting 2 sixes, and so on. Again, we could do the same kind of thing. We could see that our expected value is going to be 5, our variance is going to be 25 over 6. And I've overlaid this probability mass function with a normal 5 and 25 by 6 probability density function. What we see here is that the approximation doesn't look so good. We see that we're underestimating a lot of the values over here, and we're rather overestimating a lot of the values over here. From this, we could also go and test how good this approximation is by just going and looking at some values. So for example, the probability that we get at most 3 sixes we could find by using the p-binom function in R, where we'd go and pass the arguments 3, 30, and 1 over 6. And what we'd see is that the probability that you get at most 3 sixes is about 24%. But from this normal distribution, only about 16% of the area is to the left of 3, which seems like it's a bit of a problem here. But there's a nice modification that we can make, and the textbook refers to this as a continuity correction. I'm just going to shift the plot for the probability mass function for the binomial random variable over by 1/2 units. So instead of having the rectangle describing the probability of getting 0 sixes going from -1 to 0, I'm going to have it go from -1/2 to 1/2. And then I'm going to have the rectangle describing the probability of getting exactly 1/6 going from 1/2 to 1/2 instead of from 0 to 1. And when we make that shift, what we see is that now the approximation doesn't look as bad as it did a moment ago. We're still underestimating the probability over here, we're still overestimating it a bit over here, but the approximation is better, and really we maybe shouldn't expect the approximation to be that great because we're only looking at 30 trials. In the one that we did before where the approximation looked really good, we were looking at 5,000 trials. So as we take the number of trials to get bigger and bigger, the approximation will get better and better. Now, we could also see how well this approximation works. As before, the probability that we get at most 3 sixes is still just under 24%, but if instead of going and looking at the proportion of area that's to the left of 3, we look at the proportion of area that's to the left of 3.5, then what we see is that that proportion of area is a bit over 23%, so still off by a little bit, but a much better approximation than 16%. And in general, this is what you do when approximating the binomial distribution with the normal distribution. If you take your binomial distribution and you want to say, what is the probability that I get at most x successes, you would go and look at the proportion of area that is to the left of x plus a half. When looking at the approximating normal distribution, you would look at the proportion of area that's to the left of x plus a half. And that's exactly what we did here. We took the proportion of area that was to the left of 3.5, and what we see is that, yeah, the approximation is not too bad, even though we don't have that many trials. So here's one other example that we could look at where the approximation with the normal distribution isn't as great as we might expect, even though the number of trials is pretty big. So here, we're going to roll 3 dice 4,320 times, and I chose that number very specifically so that I'll get an expected value of 20. And we'll look at the event where we roll 3 sixes. So we'll call a success the event where 3 sixes show up, any other outcome is a failure. And from what we said before, the probability of rolling 3 dice and getting 3 sixes is 1 in 216, so under a half of a percent. So what we have here is we have a large number of trials, but our probability of success is proportionally very small. So what we have happening here is we have a large number of trials, but we have a very small probability of success. When we were looking at the first example with the coin flips, we had a lot of trials, but we also had a probability of success that was 0.5. So when we have a probability of success or also probability of failure, because they're kind of the mirror image of each other, when either one of those values is small, the approximation is not going to be as good. And if we make a plot for the normal distribution, and what we see here is that even after making the continuity correction that we made from the last example, the approximation is not as good as we would expect, especially given how good the approximation was when we were looking at the 5,000 coin tosses. So what this says is that when you're looking at a small probability of success or also small probability of failure, the normal approximation is not going to be as good as you would like. Another attribute that we have with normal random variables is that it's really easy to combine them. So suppose that you're given two random variables that are both normally distributed. X1 is going to be a normal random variable with mean -3 and variance 4, and X2 is going to be a normal random variable with mean 5 and variance 9. If we go and look at the sum of these random variables, it turns out that X will be normally distributed with mean -2 and variance 13. In other words, we add up the means and also add up the variances. And the variance, because it's a squared value, has to be something positive. So if x1 has mean mu1 and variance sigma 1 squared, and x2 has mean mu2 and variance sigma 2 squared, the sum x1 plus 2 will be a normal random variable with mean mu1 plus mu2 and variance sigma 1 squared plus sigma 2 squared. So what we have here is that the blue curve is going to be the probability density function for a normal random variable with mean 0 and variance 1. The red curve is the probability density function for a normal random variable with mean 1 and variance 2. And the green curve is going to give us the probability density function for a normal random variable with mean 1 and variance 3. So as we saw before, as the variance for a normal random variable gets bigger, the curve gets flatter. In other words, the height of the density function is going to get shorter. And we see that with the progression from the blue curve to the red curve to the green curve. Okay, so the last thing that we want to talk about is what is called the sampling distribution, and we'll see more of this when we open up R. So this relates very nicely and kind of ties together the ideas that we've had of sampling and also random variables. So if we have some random variable x, and regardless of whether or not it's a discrete random variable or a continuous random variable, we'll say that its cumulative mass or density function is going to be given by capital X, so the probability that when we observe x, we get a value that's at most little x. And suppose that we have the data set that our random variable x is based on. We could take a statistic to be some function of our data. So maybe we're looking at the variance of the height for all of the people across Canada, or we want to look at the annual income for people in Ontario and take the average of that, or we could take the median cost of a hamburger in Toronto. We could take the 25th percentile of blue jean sizes in Hamilton. We could take pretty much anything you can imagine. And what we could do is we could go and take a sample of our population and then calculate the sample statistic. So suppose you want to look at the average annual income for people across Ontario, but you didn't want to go and figure out the exact average annual income for everybody across Ontario. What you could do is go and take a sample of the people of Ontario and then use that sample, calculate the average based on that sample, and attempt to infer the actual average for all of Ontario. Now, the problems you could run into is that, kind of what we saw with sampling from before, you could run into some issues with your sample. So suppose that your sample was composed of lawyers and doctors in Toronto. You could imagine that they would have a very high annual income, whereas if you compared that sample versus a sample of farmers in Drayton or Listowel, you would wind up with a much smaller annual income. But what's nice is that we can talk about the sample distribution for the outcome of our statistic based on our sample. So to illustrate, let's suppose that we have x1, x2, all the way up to xn are going to be a sequence of observations from the same distribution. And we're going to take x bar to be the average of our x1 through xn's, so we'll add up x1 through xn and divide by n. So the expected value of x bar is going to be the expected value of the distribution that x1, x2, xn are all coming from. For example, if we were looking at the average annual income of all the people of Ontario, and suppose we knew exactly what that value was, if we took a sample of 300 people from across the province, we would expect that the average value of that sample would be the exact average annual income of everybody across Ontario. And also the variance for this value x bar is going to be 1 over n times the variance for the distribution that the x1 through xn are coming from. So again, if we had the exact values for everyone's average annual income across the province, we could calculate the variance for that population as well, and the variance for our x bar would be 1 over n times that variance for the values across the entire province. So what this says is that as you take more observations, the variance that you would get in your sample average is going to get smaller. And that leads us into two fundamental theorems that are going to conclude this part of the video, and then we'll see all of this stuff when we open up R. So we'll let x1 and x2 all the way up to some xn be a sequence of independent random variables that are all coming from the same distribution, and that distribution is going to have finite mean and also finite variance. Then as we take more and more observations, so we let the number of observations go to infinity, the average x bar, so x1 plus x2 plus up to xn all divided by n, is going to be approximately mu. Or as the number of observations goes to infinity, the average of the sample goes to the average of the population, which is going to be mu. And this is what is called the law of large numbers. In other words, if you went and flipped a coin 1,000,000,000 times, the proportion of coin flips that are going to come up heads is going to be very, very close to 50%. And in fact, if it wasn't, that would say that you've got some coin that's not actually fair. If it came out that after 1,000,000,000 coin flips, you got that 40% of them were heads, that says you've got a coin where the probability of getting heads or tails isn't actually 50-50. And what we'll see when we go into inferential statistics is how we can go and make these kind of determinations. Okay, and then the other fundamental theorem that we have is what's called the central limit theorem. And what this one says is that suppose that we have the same kind of setup. We have x1, x2, up to xn are going to be some sequence of independent random variables that are all going to be taken from the same distribution, and that distribution is going to have finite mean mu and finite variance sigma squared. If we take Zn to be the average value minus the mean of the population, all divided by sigma, so the standard deviation for our population, divide by the square root of n, so the square root of the number of observations. As n goes to infinity, that Zn value is going to be a normal variable with a distribution that's going to be a normal 0, 1. And again, we'll go and see this when we open up R. So what the central limit theorem is saying is that regardless of the distribution you started with, so long as you have a finite mean and variance, you take a sufficiently large number of observations, you subtract off the mean, and then divide by the standard deviation of your population, divide by the square root of the number of observations, that value is going to have a normal 0, 1 distribution. One thing that's very nice about this is that this ties in very nicely to what we were talking about in the very first video, where we were talking about the created order that we have. So you could pick any distribution you like, so any of the ones that we've seen or any of the ones that we haven't seen. And this result is always going to hold true. And we can see this when we go and open up R. So now what we want to do is go and open up R, and we're going to look at a couple of examples that cover some of the topics that we just saw with normal random variables and sampling distribution. Okay, so the first thing that we're going to do is I'm going to look at a normal random variable with mean 19 and variance 9. I don't know, I thought I would just pick some kind of different numbers so we could see that there's no voodoo going on with picking nice numbers. Okay, so the first thing that we can see here is that we're going to call p norm of our mean plus a standard deviation, and we're going to set the mean for our normal random variable to be the variable mean, so 19, and our standard deviation will be 3 here. When you use the normal functions in R, you want to make sure that you're using the standard deviation as opposed to the variance. And then we're going to subtract off p norm of the mean minus the standard deviation, and again set the mean to be equal to our mean value of 19, and the SD variable, or the SD parameter, is going to be our standard deviation of 3. So remember that p norm is p norm is going to return the area that is to the left of the value given with the mean and standard deviation parameters here. So we're looking in the first one for the area that is to the left of the mean plus 1 standard deviation, and then we're going to subtract off the area that is to the left of the mean minus a standard deviation. So this will leave us with the area in between the mean less a standard deviation and the mean plus a standard deviation. And we get is what we just saw from a few minutes ago. We get about 68%. Okay. So then what we're going to do is we're just going to go and plot our normal distribution. Right, so what we see is that we would have our bell curve function. It would be centered at 19, and the standard deviation here in this case would be nicely 3. Okay. So then we could see is p norm of 22. So this is going to give us the area that is to the left of the mean plus 1 standard deviation. And we would get about 84%. And we could repeat this for p norm of 25 and 28. So this would be the mean plus 2 standard deviations, mean plus 3 standard deviations. And what we see is that if we compare these 3 values to the following 3 values, we get the exact same. So these, the second pair of 3 values is the p norm for a normal 0, 1 random variable. So mean 0, standard deviation 1. And this kind of illustrates very nicely what we were saying is that whenever you're given a normal random variable, if you subtract by the mean and divide by the standard deviation, you collapse your normal random variable with whatever mean and variance you were given down to a normal 0, 1 random variable. And that's what we see here, is that for our normal 0, 1 random variable, about 84% of the area is to the left of 1, so the mean plus a standard deviation. 97.7% of the area is to the left of 2, so the mean plus 2 standard deviations, and 99.9% of the area is to the left of 3, so the mean plus 3 standard deviations. And that's what we had here with 22, 25, and 28, where we took the mean to be 19 and the standard deviation to be 3. Okay, so the next thing that we want to do is go and look at using the normal distribution to approximate the binomial. So I'll go and take n to be 100, p, we'll change p. Taking p to be 0.5 is too easy, or we've seen it enough. We'll take p to be 0.6. So we'll do some binomial setup where we're going to do 100 trials and our probability of getting a success is 0.6. I'll just say that my dev is 3, so that's how many standard deviations we're going to go on either side. Our mu for our binomial random variable will be n times p. The sigma, so the standard deviation for our binomial random variable will be our n times p times 1 minus p. So trials times probability of success times probability of failure. And then we're just going to go and load up some variables for the plotting. Okay, and now we're just going to call our plot. And what we see here is that we've gone and approximated the binomial distribution, where we've taken 100 trials, probability of success of 0.6, and the red curve is giving us the normal probability density function at a bunch of points, and they're corresponding with the blue rectangles here that are coming from our binomial distribution. So again, what we see is that we have a reasonable probability of success. So we saw that in the example, when you pick the probability of success to be either close to 0 or close to 1, things break down a little bit. And if you take n, the number of trials, to be not that big, so we saw an example with 30 trials where things didn't go great, but so long as you get that number of trials up a little bit, so here we have 100, the approximation looks pretty good. Okay, and then the other things we could see here is that continuity correction. So p binom of 45, let's call 55. So that tells us that if we take our n and our p as given, the probability of getting at most 55 successes is going to be a bit under 18%. And then we could look at some p-norm values. So the first thing that we would want to try if we were looking at the normal values is compare against p-norm of 55 I guess in this case. So if we just went with the maybe naive assumption that we could ask for p-norm of 55 with our mu and sigma, we would get 15%, which does seem rather low. But then if we make that continuity correction and we look at p-norm of 55.5, so we get all of the area that is to the left of 55.5, we would get 17.91, which is pretty close to the p-binom value. And then just to see that 55.5 is going to do a really good job of approximating our p-binom of 55 value, if we went for p-norm of 56, we'd be overshooting the value by a fair amount. Okay, so then the next thing that we want to do is see an example of the law of large numbers in action. So here what we'll do is we will go and sample from binomial distributions. So what we're going to do here is we are going to take So what we're going to do here for our law of large numbers is we're going to take 100,000 samples of taking the mean of binomial distributions, where our number of trials in the binomial distribution is going to be 300, the probability of success is going to be 60%, and we're going to take samples of size 10, 100, 1,000, and 10,000, and then what we're going to see is how the means and the variances line up based on what we said from our law of large numbers. And now what we want to do is just look at our mean and variance for these binomial samples. Okay, so what we would see is that in all of them, the means are pretty close to 180, which is what we would expect. We're taking 30 trials and a probability of success of 60%, so you would expect 180 trials or 180 successes. And what we see here is that, well, actually, the closest one to the correct answer is 1,000 samples. The one for 10,000 is a little bit further away. There's probably some round-off error going on here, because we see that we're given the answers to 4 decimal places, so I would suspect that the 1,001 and the 10,001 are maybe closer than it could suggest from the numbers we're given. So saying like the 1,000 would give 180.0004 and the 10,000 would give 180.0005, something like that, but I'm not sure offhand. Okay, and then the variance. So what we see here is what we would expect based on the results we had when talking about our law of large numbers. As we increase the number of samples that we're taking from the binomial distribution by a factor of 10, our variance decreases by a factor of 10 because there's that 1 over n factor in the variance. The other thing that I should point out is that here we're calling R binom. So the R binom is the fourth of the major functions that you can call for dealing with probability distributions. And what R binom does is it draws from the distribution this number of samples. So R binom of 10 with 300 trials and 0.6 successes will go and give you 10 outcomes from the binomial distribution with 300 successes and a probability of success of 60%. And we would get, in this case, these 10 outcomes. Okay, and then we want to see an example from the central limit theorem. So here what we're going to do is look at a Poisson random variable. Let's take our lambda to be 11. So we'll look at a Poisson random variable with a mean of 11. So remember that for a Poisson random variable, the lambda was giving us the average number of occurrences in some time interval. So maybe you're running a shop where you get an average of 11 customers per hour, something like that. Okay, so then we'll do the same kind of thing as we did just a moment ago. We will go and take various numbers of samples for our Poisson random variable. So again, here we'll call our Pois, which will generate, in this case, 10 Poisson outcomes with mean lambda, 100 Poisson observations with mean lambda, and so on. Okay, and now what we want to do to wrap up here is just go and plot our various outcomes for these Poisson distributions against standard normal random variables. So for the first one, we know what our mean and variance are for the underlying Poisson distribution, in this case lambda for both. And we know from our central limit theorem that if we take the outcomes from our Poisson distribution, so we know from our central limit theorem that if we take the Poisson outcomes, we subtract off the mean of the underlying distribution, so lambda, and then divide by the square root of lambda divided by the number of samples used to make the mean. So in the first case 10, and then in the other cases 100, 1,000, and 10,000, we'll get a standard normal distribution as n increases. So we can see here is that a plot of the standardized Poisson outcomes against a standard normal distribution. Not too bad actually. In the middle, it's maybe off by a little bit, but outside of the couple of values here, yeah, not too bad. And probably if we went and just split the difference between these two, we'd get something that looks pretty accurate, and that's for taking only 10 samples for the Poisson distribution. Okay, and if we take 100, what we see is something that conforms even better to the normal distribution. And then we can also do 1,000 and 10,000. And what we'll see is that the results are pretty similar. What we see for 1,000 is that looks pretty accurate. And for 10,000, same idea. So again, as n is increasing, the adherence that we're getting to the standard normal distribution is getting better and better. And this tells us that we get what we would expect. And there's nothing special here about taking a Poisson distribution. We could have taken any of the distributions we've seen so far or any of the ones we haven't seen. Okay, so that concludes everything that I want to say here for the normal distribution and the sampling distribution. And I will see you in the next video or on any Zoom call. Bye.